Page 120, section 1.5. 120, section 1.5. On 1.5, we're talking about inverse functions. Inverses are basically just things that undo each other, right? Like we've always learned that the inverse of adding 5 is subtracting 5, right? What undoes adding 5 is subtracting 5. What's the inverse of multiplying by 2? Dividing by 2. It's just whatever it takes to undo whatever the process is. There are all kinds of everyday examples too. I mean, you can take a step forward and you can take a step back. They undo each other. They take you right back to where you started from. You can tie your shoe and untie your shoe. You can open the door and close the door. You can have a gain of 5 yards on the play and a loss of 5 yards on the play. They're inverses. They undo each other. They take you back to where you started from. And the same thing is true in mathematics. So there are some inverses that, like we were just saying, you automatically know what it is. Like if they tell me f of x is equal to 3x, find the inverse, I just look at that and go, well, if x is being multiplied by 3, what would undo that? What's the inverse of that? Dividing by 3, right. So literally the inverse of that function would be x divided by 3. So if I'm looking for what's the inverse of multiplying by x by 3, it would just be dividing x by 3. The notation that we're going to use for inverse, you'll see right here, it's just f to the negative 1 of x. That's what it looks like anyway. That is our notation for inverse. Now, I know typically we use a negative exponent to show that we're supposed to move across the division bar, you know, like x to the negative 1 is 1 over x. But we'll be able to tell from the context that we're in whether they want us to use a negative exponent or whether they're referring to an inverse. You know, we don't normally see f of x like a whole function raised to the negative 1 when we're talking about negative exponents type thing. And in the context of what they ask us to do, we'll be able to tell, hey, they want me to find the inverse, even though that notation is the same. So in this situation, we were able to just look at it and tell what the inverse is, but that's not always the case. Like if you look at the next one, we've got f of x is equal to 5 minus 3x divided by 2. Now I can look at that and say, okay, what's going to undo the dividing by 2? Multiplying by 2. What's going to undo adding 5 to something? Subtracting 5. What's going to undo multiplying x by a negative 3? Dividing x by negative 3. So I know that I need to do those 3 operations, but I'm just not really sure what order to do them in and exactly how to write that. And so if I get to a function that maybe is a little more complex and I'm not sure exactly how to do it, I do have a two-step process that I can use for finding the inverse. Step number 1 is switch x and y, and then step number 2, solve for y. So if we take our function, we've got f of x is equal to 5 minus 3x over 2. I want to switch x and y. I have an x, I don't have a y. Where's y? It's in disguise. F of x, yes. F of x and y are the same thing. So if you want to write it that way first before you switch your x and your y, that's fine. Okay? So step number 1, we're going to switch x and y. So literally, I'm going to put x where y was, and I'm going to put y where x was. Switch x and y. Then step number 2, I'm going to solve for y. So basically, I just want to get y by itself. So if I were trying to get that y by itself, what do you want to do first? All right, so let's multiply both sides by 2. That was one of the things we said we knew we would need to do anyway. What do you want to do next?
Subtract 5.
All right, so let's subtract 5 from both sides, and then what? Divide by the negative 3. So I'll end up with y is equal to 2x minus 5 over negative 3. That is my inverse. Switch x and y and solve for y. Now, we've seen this before, but there are usually several different ways that you can write your answer. So like I get one answer and I look in the back of the book and the answer they have is different than mine. Don't automatically assume that your answer is wrong. here are a couple of other ways you could have written that same function. Like you could go through and divide everything by that negative that's down there in the bottom. You've got a negative 3. If you divide everything through by that negative, you would say 2x divided by that negative is negative 2x, and negative 5 divided by that negative is positive 5, and then that negative in the bottom would go away. They also, in the back of the book, almost will never leave a negative out in front, so they probably would have written that instead of negative 2x plus 5, they would have written it as 5 minus 2x. So, you know, I get this as my answer, and I look in the back of the book, and it's this, and I'm like, man, I got that completely wrong. Nope, it's absolutely right. It's just written a little differently. So check and see if maybe your answer could simplify to theirs, or their answer could simplify to yours before you assume that you've done something wrong. Okay? So that's how we can find the inverse. All right, the next thing that they tell me about inverses, in addition to basically an explanation and a definition there, is they tell me that we can also verify that two functions are inverses of each other algebraically. So they had given me f of x, and I just created what I think is the inverse of f of x. How could I verify that? How could I check that? Well, if two functions, f of x and g of x, genuinely are inverses of each other, if you do a composition of those two functions in any order, they will cancel each other out and just leave you with what you started with, x. That's the definition of an inverse, right? Two things, they undo each other and take you back to where you started. I started with x, I plugged it into one function, I plugged it into the other function, they undid each other and just left me with x that I started with. You should be able to do that in either order. You should be able to do the composition of f of g of x or the composition of g of f of x, and in either case just be left with x. So if they say find the inverse, they want me to switch x and y and solve for y. But if they give me the function and the inverse and they say verify these two are inverses of each other, they want me to do the compositions, right? So let's check those functions that we were just working with and make sure that they really are inverses of each other by using this method. So let's start with f of g of x. G of x was 5 minus 2x over 3, so let's just replace g of x with what it's equal to, 5 minus 2x over 3. Now I have f of that fraction. So f of that fraction says put that fraction in the place of x in the f function. So that would be 5 minus 3 times the fraction over 2. 5 minus 3 times that fraction over 2. So one more time, we had f of g of x. We replaced g of x with what it was equal to, 5 minus 2x over 3. F of that fraction says put that fraction in the place of x in the function. So that was 5 minus 3 times the fraction over 2. 5 minus 3 times the fraction over 2. All right, so now we just want to simplify. If you'll notice, our 3's will cancel each other out. And that would leave us with 5 minus the quantity, 5 minus 2x over 2. I need to distribute that negative through that quantity. So if I do, then I would have negative 5 and positive 2x. So 5 minus 5, of course, would drop out. And 2x over x, the 2's would drop out. And that would leave me with just x, which is good, because that's what the theorem says that we should get. All right, let's go the opposite way. Let's say that we had g of f of x, all right? If we had g of f of x, first off, I'm going to replace f of x with what it's equal to, which is just 5 minus 3x over 2. So g of that fraction says put that fraction in the place of x in the g function. So I'm going to come up here and it would be 5 minus 2 times the fraction over 3. 5 minus 2 times the fraction over 3. All right, so what you want to do first to simplify that? All right, let's get the 2's to drop out. So then we'll be left with just 5 minus the quantity, 5 minus 3x, all over 3. All right, then what? Okay, distribute the negative, and when I do, then my 5's will drop out, right? And be sure when you distribute that negative that you do negative 5 and minus a negative, so plus 3x. All right, then what? Cancel out the 3's, and we'll be left with just x. So yeah, when we did f of g of x, we got x, and when we did g of f of x, we got x. So if they ask me to verify or prove that two functions are inverses of each other, then that's what I can do. And I do need to do it both ways. I need to do f of g of x and g of f of x. All right, now that's how we can verify our functions algebraically. We also can verify inverse functions graphically. So let's look at some of the traits of inverses when we graph them. All right, let's go back to those same two functions we've been working with. F of x was 5 minus 3x over 2. And then we had found the inverse to be 5 minus 2x over 3. Okay, so let's graph them and just see what we come up with. So I picked some random values over here for x. So if we take 1 and put it in the place of x here, we would get 5 minus 3 over 2. So 2 over 2, which would give us 1. How about if we take negative 1 and plug it in? What are we going to get? 4. And what if we take positive 3 and plug it in? Negative 2. So let's plot those points. I've got 1, 1, negative 1, 4, and 3, negative 2, and there's the graph of my original function. All right, then let's graph the inverse. Again, I've just got some values here for x. So if we go through and we put 1 in the place of x, what are we going to get? If we put 4 in for x, what do we get? Negative 1. And if we put negative 2 in for x, what do we get? 3. Okay, hang on just a second. You notice anything remarkable about those two xy charts? They're just flipped, yeah. Remember the way that we created the equation of the inverse? We switched x and y, right? So that's why whatever is x in the original is y on the inverse, and whatever is y on the original is x on the inverse. Literally, I can take the ordered pairs of my original function and flip them, and I will get the ordered pairs of my inverse. So that's one really cool thing about inverses. That would be one way then that I could verify this graphically, because I could put the equation in y equals and look at a table, and then I could put the inverse in y equals and look at a table, and x and y should be switched, right, in the table. That'd be one way I could do it. All right, let's go ahead and graph what we just got. We had the point 1, 1. We had the point 4, negative 1. And we had the point negative 2, positive 3. So that gave us that red line. Now, when you graph a function in its inverse, they will reflect in the line y equals x. Now, y equals x, we should know what that looks like. That's one of those 6 graphs from page 100. That's the diagonal line that goes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. That's y equals x. That's what we've got dotted on here. Y equals x is an axis of reflection for a graph and its inverse. So basically the idea is if I used wet paint and I painted that blue line right there, and then I folded my piece of paper on this dotted line y equals x, what would get transferred over from that wet paint is this line right here. So basically, when I folded it on my dotted line, this part of the line would transfer here, and this part of the line would transfer here. So a graph and its inverse reflect in the line y equals x. Now, we're going to do this by hand. We're not going to do this on the calculator, but just fun facts for you to know and grow on. You can get your calculator to draw an inverse for you. You can just watch this. You don't have to get your calculator out. But if you go to y equals and you put in that original equation, f of x, 5 minus 3x over 2, and you graph it, here it is right there. That's that same line that we had graphed before. I'm also going to go ahead and put that reflection line in just so that you can see it. And I'm going to make it bold. So I went into y2 and I just put in y equals x, that line of reflection. And there it is, that bold reflection line. Okay? If I go to my draw menu, so if you go to program, its second program is your draw menu. If you go to your draw menu and go down to number 8, you can tell your calculator to draw the inverse of something. So I'm going to tell it to draw the inverse, and I either could retype this equation, 5 minus 3x over 2, or I can just say draw the inverse of what I have in y1, either one. When I do that, my calculator will literally go draw in this inverse right here. I don't even have to tell it what the equation of that function is. That's a really cool thing, because basically all it has to do is just take the ordered pairs and flip them, right, and make a new XY chart from that. So you'll notice your calculator can in that way generate a graph identical to the one that we just created a second ago. Okay? All right, the next thing that they talk to us about is one-to-one functions. A function is one-to-one if, first off, of course, it has to be a function in order for it to be a one-to-one function. So it's a function, and it has an inverse that is also a function. A function's one-to-one if it's a function, and it has an inverse that is also a function. So what was the fast, easy way that we could tell if we had the graph of a function? Some kind of test that we did. Close. Vertical line test, yes. So we would go through and we would draw vertical lines, and if we only hit our graph in one spot or less, then it was a function. But if we hit our graph in more than one spot, it was not a function, because that would be two x values that are the same, right? And you're not allowed to have any two x values the same. So I could look at that and go, okay, yes, that is a function. Now I want to see, is its inverse also a function? If its inverse is a function, that means that its inverse can't have any two x values the same, right? So I literally could come over here and I could do my little dotted line of reflection, you know, and I could reflect this thing over and draw the inverse and do the vertical line test on the inverse. Absolutely could do that. But here's a faster way. If I want to know if the inverse has two x values the same, and x and y switch places on the inverse and the original, that would be where the original has two y values the same, right? Let me say that one more time. If I want to make sure that my inverse doesn't have two x values the same, and on an inverse and the original, x and y just switch places, that would be where on the original, I have two y values the same, right? So instead of even having to draw the inverse, all I have to do is just look at the original and say, does the original have two y values the same? I could check that with a horizontal line test. So if I draw a horizontal line test and I hit my graph in more than one spot, that means the original has two y values the same. So the inverse, when I flip, would have two x values the same, right? No two x values the same for a function. So I just found out that my inverse is not a function. So for me to have a one-to-one function, my original and my inverse both have to be functions. This original was a function, but its inverse was not, so it was not one-to-one. Here's the simplest way. If you pass the vertical line test and the horizontal line test, your function is one-to-one. If it doesn't, then it's not. So if your function passes a vertical line test and a horizontal line test, it is one-to-one. If it doesn't, then it is not. Okay? So this one was a function. It passed the vertical line test, but it did not also pass the horizontal, so it's not one-to-one. All right, look at the next one. For the next one, does it pass the vertical line test? Yes, so it is a function. Does it also pass the horizontal line test?
Yes.
Yes, so that means its inverse is also a function. Therefore, it is 1-to-1. Because it passed the horizontal and the vertical line test, that means it and its function inverse and its inverse are both functions. Last thing that I want to mention to you, although it's not really an example here in the textbook, is there are some times that instead of giving you an equation, they'll give you a graph. And they'll ask you to draw the inverse of that graph. You know, we did that up here. They gave me something and I drew the inverse, but I had an equation to go by. So I could do it algebraically if I want to. But when I get down here, I don't have any algebraic equation. All I have is just a graph, and it says if this is the graph of f of x, draw the inverse. All right, so here's what you could do. Some of you are very visual, and you just look at that and you're like, okay, there's my line of reflection, so I just come over here and it's basically just going to look like that. There it is. I got it. I'm done. Fantastic. For the rest of us, let me give you a way that you can do it if you can't envision it that way. I could go through on my original function and just identify some key points, okay? Like I went through and said, that's at 0, 2, that's at 2, 4, and that's at 4, 5. If I have the point 0, 2 on my original function, what's that point going to be on the inverse? The opposite, right? The flipped value. What would that be? 2, 0, right. So if this point is 0, 2, the inverse point is 2, 0. If this is 2, 4, inverse point is 4, 2. If this is 4, 5, inverse point is 5, 4. So I could then give myself a couple of points to use as guides, and then that makes it easier to graph that inverse. Okay, so here is your homework for tonight on section 1.5.